Hi there, I'm Danny Jones. I work at the British Antarctic Survey. Thanks very much for your interest in our work. Here, I'd like to discuss the application of a particular unsupervised classification technique to the Weddell Gyre region of the Southern Ocean. Big thanks to my collaborators shown below for all of their efforts. Big thanks to the session organizers for hosting, and big thanks to UKRI for funding this work. In recent years, a few groups have attempted to apply unsupervised classification, which is a type of unsupervised machine learning, to the identification of different thermohaline structures. I've listed a few of the relevant papers that I'm aware of below. My apologies if I missed any of them or if I missed yours. Here, we are using a combination of Argo float and ship-based CTD profiles. On the top left is a histogram of these profile locations in a grid for all of those profiles with data covering the top 1,000 meters of the ocean. You don't see anything really on the shelf here because of that depth range restriction. In the middle, we've got three figures: depth on the vertical axis, pressure as recorded by the instrument, but converted into depth. And you've got conservative temperature, absolute salinity, and the potential density. So the gray lines, those are individual profiles. That's a sample of the profiles there. And the dashed and solid lines, that's the 25th percentile, the median, and the 75th percentile, respectively, and the n being the total number of profiles available. So we'd like to look for classes or subgroups in this thermohaline data using what is sometimes called a profile classification model. I'll explain that method a bit more soon, but the short answer is that, yeah, we can identify classes in this data set. This classification method is probabilistic, and we can use that probabilistic information in our classification efforts. Specifically, the coloring scale here is the I metric, which is a measure of how likely a point is to be at the boundary between two classes. The dark colors indicate that that point, that profile, is more likely to be clearly within one of these classes. You can read more about that in Simon Thomas's work in the Ocean Science Journal from last year. Let's have a really quick look at the classes. We've got an Atlantic Agulhas class, an Indian Agulhas class, two Antarctic circumpolar classes. One is sort of north of the subantarctic front, and the other one is a bit more in the ACC. But for this talk, I'm not really interested in any of those. I'm really interested in the bottom one, the class that is kind of subantarctic, the one that's roughly south of the polar front. I want to see if we can actually subclassify this class, even further. How are we going to do that? How do we do this? The method is you transform the temperature and salinity profiles from depth space into principal component space first. Well, before that, let me back up one step. Before that, you scale all of the conservative temperature values, all of the absolute salinity values on each one of the pressure levels, combine that into a single long kind of record, and you transform that into principal component space. That reduces the computational complexity of the problem. So now, instead of representing each TS profile as a large number of values and all the different pressure levels, you're representing each profile as just, in this case, 6 different principal component coefficients. This plot in 3D space here, you should think of as a projection into that 3-dimensional space. All right, next, we'd like to cluster the points in this abstract principal component space. So you've got this kind of shape here, this kind of interesting shape in principal component space. That's where you do the clustering. There's different methods for this, but one of the standard methods is to try to represent this data distribution as a linear combination of Gaussian functions. Here's what it looks like. Here's a 5-class example where we have represented the data distribution in the space, again, using 5 different multidimensional Gaussian functions. And the color shading indicates to which class each point has been assigned. Okay, yeah, so that is roughly how the method works. Again, there are many different ways to do it, but that is the essential kind of statistical approach. You're trying to fit this data to that Gaussian distribution. Back to our research question, can we further subdivide the near Antarctic class, this one here? And I just wanted to give a quick reminder. Here's the circulation context that we're working with here. There's the Antarctic Circumpolar Current flowing from west to east. We've got intrusion of circumpolar deep water on the eastern edge of the gyre. The central gyre here, that's got Weddell Deep Water circulation. And then we have kind of near coastal waters, near coastal circulation that's affected by both ventilation and under ice shelf processes. And up here, you'll find the Weddell Scotia confluence waters, which we'll come back to in a minute. So that's just the kind of circulation context that's good to keep in mind here. One free parameter in this method is the selection of the number of classes. there isn't necessarily a general global answer for the kind of correct number of classes. You can get some statistical guidance. There are statistical techniques you can use to get a bit of a constraint on the number of classes, but they won't necessarily give you an ambiguous single answer. This is an example of one of those criteria, the Bayesian information criteria. You basically want to look for a minimum in this. As the likelihood of your statistical model increases, the BIC score drops. And then at some point, there is overfitting. There's an overfitting penalty term, which starts to kick in as you add more and more classes. Ideally, you'd have a minimum, but I don't hardly ever see a clear minimum in ocean data, I think because it's very highly correlated. Really, if you pick something within this kind of range, in this case between sort of 4 and 10, you are picking something that's consistent with the statistical guidance. You can use this elbow method also, which I quite like, the elbow method where the change in BIC starts to become very small. So you can see as you move from 3 to 4 classes, there's a drop. As you move from 4 to 5, there's hardly any, at least in the mean here. This is a statistics over many realizations of this BIC calculation. So that is one way to pick. Conceptually, if you pick fewer classes, you're capturing fewer dominant structures in that data set. It's simpler to interpret, but you are missing some details there. So that's a choice that you could make depending on the application that you're working in. If you include more classes, yes, you'll capture more subtle structures, but it will require more complex interpretations. Yeah, so let's get back. What does this 4-class model look like when we actually apply it to the data? Well, we've got these 4 dominant structures that pop out. I've plotted them in the iMetric there, and I've plotted some fronts from Kim and Orsi as a reference on top of there. The subantarctic front, the polar front, the southern ACC front, and the southern boundary front are the 4 that you're looking at there. The central Weddell Gyre stands out as a particular class. It does have some higher iMetric values over here on the boundary, possibly where the circumpolar deep water is intruding in. That might be a signature of that. So I really do kind of like how coherent that is. It's interesting. You have the second class, confluence and shelf waters, still south of the southern boundary front, but it is sort of here the confluence of the water that is coming from the south that has been affected a bit more by shelf processes, and also just kind of Scotia area waters here. And then you have some profiles that are affected by ventilation over on the eastern edge of this domain as well. Now, then you also have 2 transition classes. You have these 2 Antarctic circumpolar kind of classes as you transition from the central gyre up through the ACC. You've got one that's south of the southern ACC front, and you have another one that's north of the southern boundary front, roughly. They do have a little overlap. That's okay. That's expected. There's some mixing there. There's not necessarily a super clear boundary or separation between them. That's one of the things that you get out of this more probabilistic view of how the profiles are distributed. Let's look at each profile in a bit more detail. We'll spend at least a little bit of time on each one of them. Here's the central Weddell Gyre. Again, you're looking at the statistics and the distribution of the profiles that belong to that class. Here in the conservative temperature, you can see it's got very cold surface temperatures. It has the coldest surface temperatures of all of the classes with a relatively sharp picnic line. As you'll see in comparison with the other classes, that picnic line is relatively sharp. The other ones are a bit gentler. And like I mentioned on the previous slide, there does seem to be a bit of intrusion of circumpolar deep water on that eastern edge. Here's that confluence class, the confluence and shelf south of the southern boundary front. Still very cold, very fresh. You see the cold temperatures there and warmer temperatures below, the temperature inversion. Like all of these classes, that's stabilized by the fact that the surface is fresh and the interior is salty, so that you do ultimately have a stable water column like you would expect, less dense water sitting on top of more dense water. So yeah, this is cold and fresh water. It's got a relatively gentle picnic line compared to the other ones, at least in the statistics. And yeah, it's affected by those near shelf ventilation processes and possibly affected by what's happening underneath the ice shelf, at least in this part of the domain there. That's kind of, you see these Weddell Scotia confluence waters. That might be what we're identifying here. Here's another transition class south of the southern ACC front, a little bit warmer. Now you can see them getting a little bit warmer. We've got relatively shallow winter water temperature minimum compared to the next transition class that I'm going to show you. So pay attention to that. The winter water temperature minimum is a little bit shallower here. The mixed layers are a little bit shallower. This is affected by mixing of circumpolar deep water and winter water. That's a hypothesis we're developing here, and I'll show you a bit more about that. We think that this class is affected by that mixing between circumpolar deep water and winter water, whereas the northern class we think is less affected by that. This is the class that we think is less affected by mixing between CDW and that winter water. Got a relatively deep winter water temperature minimum compared to the previous class, especially deeper mix layers. And it's like we said, I'm kind of repeating myself, but it's relatively unaffected by that mixing of circumpolar deep water and winter water. Can we confirm that? Let's see if we can confirm that by looking at a couple of temperature and salinity diagrams. Lots of different kinds of oceanography are valid, but there's something satisfying about a TS diagram. So the difference between these two transition regions is partly explained by the presence or absence of mixing between those the winter water and the circumpolar deep water. Here's the class that is affected. And you notice I've got this region circled here. This region in TS space, this connection between these two end members, was highlighted in this paper by Evans et al. In 2018. So notice how in the class that is thought to be affected by that mixing, we do see some profiles. We do see that the profiles occupy some of that space in this TS space, whereas in the class that we think is relatively unaffected by that mixing between winter water and circumpolar deep water, the profiles don't really pass through that part of TS space. So we have taken that to be an indication that that's one of the differences between those two classes. Now, if that hypothesis is correct, then what you might expect to see is that you'd expect to see the locations of freezing of sea ice in the winter associated with brine rejection and mixing of CDW and winter water. You would expect that freezing line to roughly line up with the more southern class, the class that we think is more affected by that mixing of circumpolar deep water and winter water. And the top plot there, what you're looking at is the sea ice edge, or rather the location where the freezing of sea ice has the biggest effect on the salinity there in the winter from the Southern Ocean state estimate. And roughly, okay, it's not perfect, but roughly that line where the freezing is occurring does line up reasonably well with the locations of the southern class. It certainly is kind of more biased towards that southern boundary front, which I'm showing here in yellow, which is kind of where that southern class is more kind of centered around. Certainly this seems to be the case on the western side of this domain. Not as much on the eastern. I think the eastern is a little bit of a different story potentially. So I'm mainly focusing on the western side of the domain for this. Okay, so in summary, in recent years, unsupervised classification has been emerging as a useful data analysis tool in oceanography. There's a review paper by Micah Sonnewald and others, I'm on there as well, from last year talking about general machine learning applications in oceanography, including unsupervised classification. And in this particular analysis, when we apply this technique south of the polar front in the Weddell Gyre kind of sector of the Southern Ocean, we can identify these 4 different coherent types of thermohaline structure. And just a point as we close here, there is no single correct global profile classification model. The construction of the model should be guided and informed by the objectives of the study that you're doing, the level of detail that's required, and the available data. This is kind of consistent with an argument that Chris Chapman and others made in reference to thinking about fronts in the Southern Ocean, that there isn't necessarily a single global correct definition, that we might need to get more regional in our approach. Okay, again, thanks very much for listening and for your interest. Thanks to the organizers, thanks to the funders. And yeah, okay, take care. Talk to you later. Bye-bye.